Greetings, my name is Matthew, and in this video we're going to talk about trigonometric functions that are defined for any angle. And we're specifying any angle here because before this, or up until now, we've really been focusing on 30, 60, 90 triangles and 45, 45, 90 triangles. So angle measures that look like pi over 6, pi over 4, pi over 3. Pi over 2 is one of those multiples that we run into, but we have not talked at length about that yet. And I'm going to mention it in this video. And then in a later video, when we look at the graphs of the sine, cosine, and tangent functions in particular, I think those conversations are going to make the evaluation of the quadrantal angles considerably easier. So I'll mention that when we get there, but for now, let's take it from the top. We're seeing a familiar diagram here, and my organization system is falling apart over here. Here we go. All right. This diagram on the left is using x and y for the leg lengths of our triangle. We have talked previously about it maybe being a good idea instead of using x and y, although that does help us see which direction those leg lengths are moving in. This would also be considered the adjacent side. This is the opposite side, and r is the hypotenuse. So, in keeping with our conversation about SOHCAHTOA, I'm still going to define these 6 trig functions as opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and then the other 3 functions are the reciprocals of those 3. Hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. Remember, in the previous section we talked about the equation of the unit circle. You can also find or sort of generate the equation for the unit circle by using the distance formula. In this case, the distance formula, in order to calculate r, so we're moving a horizontal distance of x, a vertical distance of y. Based on the Pythagorean theorem, we can say that r, the hypotenuse, would then be equal to the square root of x squared plus y squared, or the adjacent side squared plus the opposite side squared. If our theta value is not acute, trig functions may take on negative values, and we have seen that already, where we evaluate a trig function and we get a negative answer because the adjacent or opposite side ends up being negative. So here we're going to look at a specific point on the terminal side of an angle theta, and we're going to evaluate all 6 trig functions. We are never going to know what theta is in this particular problem. Up until now, for the most part, we've known what theta is. It's either 30, 60, or some kind of multiple thereof, or a multiple of 45, regardless of what quadrant it puts us in. So, since we're being given a specific point, let's draw a little sketch. So we're going to the left 12 units. Why is my pen not working anymore? Come on now. That is strange. There we go, negative 12. Doesn't look like a 12, but it is, I promise. And we're going up 5 units, not to scale, of course. So our point is, I don't even like that. I can't handle it. Something more like this, having gone up 5. And then you can draw in your radius out to that point, and drop your altitude to the x-axis, always drawing a line from the end of your hypotenuse to the x-axis, in order to create a little right angle there. And let's then go in and label these as actual side lengths. So this side has a length of negative 12. Vertical is positive 5. The negative really is telling us the direction, so the negative horizontal direction. By the Pythagorean theorem, square root of a squared plus b squared, well, let's not say it that way. Let's actually reference what we already wrote down, that r equals the square root of x squared plus y squared. 5 and 12 are your x and y values, and if you do the arithmetic on that, you'll get the square root of 169, which is equal to 13. Some of us know the 5, 12, 13. That's one of the famous, I suppose, Pythagorean triples. There's the 3, 4, 5 triangle, 5, 12, 13, 7, 24, 25, and the 8, 15, 17 triangle. So we'll see multiples of those as we go along. Now that we have ourselves a good diagram, we might also note that our theta value is larger than 90 degrees, larger than pi over 2 radians, and is rotating us all the way around into the second quadrant there. That's a poorly drawn theta that I just made. But more typically, we focus on this reference angle, theta prime, that's inside our triangle, and it's the angle nearest the origin. So our opposite side is going to be the 5. The adjacent side will be the 12. The hypotenuse is clearly the 13. And we've got all the information we need to evaluate the 6 trig functions. In my mind, I feel like getting the diagram dialed in just right is the more challenging part. That's the place where you want to go really slowly. Once it comes time to evaluate the trig functions, these are pretty easy, especially if you're coming into a trig class or a pre-calculus class already knowing SOHCAHTOA. So you've got opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. With a good diagram, all you're doing is filling in the blanks on that. Just write in your O, H, and A values, and you're good to go. So here we've got 5 over 13, negative 12 over 13, opposite is 5, that's an equal sign, over adjacent, which is the negative 12. So these are your first 3 solutions. Cosecant, secant, and cotangent are the reciprocals of those first 3 answers. I'm going to leave you to fill those in. I don't think you need me to write them down for you. So that's the process. The diagram, super important, making sure that the 12 ends up being negative, realizing that you're determining opposite, adjacent, and hypotenuse based on the reference angle. So looking at that theta prime, the opposite side being across from theta prime. So there's another opportunity for an example there, but I want to keep this video a little bit shorter than some of my previous ones already. Signs of trigonometric functions. So if you went through and you looked at and evaluated a lot of trig functions, even if you just evaluated the sine function for an angle measure that's in the first quadrant and in the second quadrant, and then one in the third, one in the fourth, and so on, you went around and around and did that for sine, cosine, and tangent, and the reciprocal functions, you could make yourself a list. And a good sort of consolidated way to remember which functions are positive where is with a mnemonic that some people like that says, all students take calculus, which is not really the truest statement of them all. I've modified it, and I like to say ambitious students take calculus. And we start labeling the 4 quadrants, starting in the first quadrant, and if you don't remember, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And so we're going to say that ambitious students take calculus. And that mnemonic helps us remember which functions are positive in each quadrant. All of our functions are positive in the first quadrant. So if you take the sine of an angle measure that's in the first quadrant, you're going to get a positive answer. If you take the cosine of an angle measure that's in the first quadrant, your answer is going to be positive, and so on. The sine function is the only one that's going to return a positive answer if your angle measure is in the second quadrant. It's not the only one. Of the 3 primaries, it's the only one. Cosecant, its reciprocal function, certainly the reciprocal of a positive number is still a positive number, so its reciprocal function will be positive in the second quadrant also. The tangent function and its reciprocal function, cotan, and cosine and its reciprocal function, secant, will be positive in the fourth quadrant. There's a lot of stuff to memorize in the world. There's a lot of stuff to memorize in a trigonometry or pre-calculus class. Can you memorize all of it? Some of us can, some of us can't. I struggle with memorization, so devices like this can be helpful. We have better days and worse days, and sometimes we can remember the mnemonics and sometimes we can't. Sometimes processing's faster or slower, depending on the day. But hopefully you can use that as a tool that'll be helpful for you. So these questions are pretty easy to answer once you've got the technique. So theta is an angle in standard position. State the quadrant in which theta lies. The sine of theta is negative. In which quadrants is the sine of an angle measure going to be negative? Let's reference the visual that we had on the previous page. We know that the sine is going to be positive in the second quadrant, and we know that all of our trig functions are positive in the first quadrant, so that's where they're positive. So where is the sine function going to return a negative answer? That's in the third and fourth quadrants. So I'm going to go down here again and put a little note. Sine of theta will be less than 0 in the third and fourth quadrants. Now what about cosine? Where is it going to be positive? Well, the mnemonic says, ambitious students take calculus. So the A stands for all. I know that cosine is going to be greater than 0 in the first quadrant, so I'm going to put down a Roman numeral 1. Ambitious students take calculus. C for calculus. That's in the fourth quadrant, which means that cosine is positive in the fourth quadrant. In this question, we're interested in where cosine is positive or greater than 0, and that is in the fourth quadrant. Now, the larger overarching question in this instance is, so where's theta? It's a theta value that has to satisfy sine of theta being less than 0 and cosine being greater than 0. Well, which quadrant do these two have in common? It's quadrant 4. So however you want to highlight for yourself that it was the quadrant that they had in common, you should do that. I'm going to put a box around my final answer as I usually do. Quadrant 4 is our answer. Let's try the next one. Where is cotangent positive? Everything's positive in quadrant 1, so I love it when we're looking for a positive answer out of a trig function. Now, ambitious students take. Take happens in the third quadrant. T for tangent and its reciprocal function. So it's also going to be positive in the third quadrant. Tangent and cotangent are positive in the first and third quadrants, diagonally from each other, first and third. You'll see them enough times, my guess is you'll start to remember that. Now, secant. When it comes to reciprocal functions, I always have to kind of revert back in my mind. Secant is the reciprocal of cosine. So we want to know secant and cosine are going to both be positive in the first quadrant. So we're not interested in that one. Ambitious students take calculus. C for cosine and its reciprocal function secant, that occurs in the fourth quadrant. That's where they're positive also. So cosine and secant are positive in the first and fourth quadrants. We want to know where they're going to be less than 0, in other words, negative, so that must be in the second and in the third quadrants. Some of you are grasping this really quickly, and so my explanations seem to be slower than necessary. Some of you are very grateful that my explanations are the speed that they are. So I'm trying to cater to everyone. Just be patient. Or watch the video in an accelerated speed. You know that you can go in and bump up the speed if it's getting too slow for you. All right, so quadrant 3 is our answer there. There's a you try it example. I'm not going to do that one because I've already done a couple. My hope is that you're getting the hang of that. I want to go into sort of an elevated version of these kinds of problems where we take the two previous ideas and mix them together, find the exact value of the remaining trig functions. Here, we see that if you take the tangent of theta, you get a negative answer. So what this tells me is that the tangent of theta is less than 0, similar to the kind of problem that we just finished doing. Tangent here is less than 0, sine is greater than 0, so we need to figure out which quadrant we're in. And if you want to write a little note that says, step 1, figure out which quadrant we're in, that's not a bad idea. And as usual, the iPad is on the blink, so we unplug and we replug, and then all should be well. 3, 2, 1. I'm getting good at that. All right, so where is tangent positive? We just talked about this. It's positive in the first and third. So where is it going to be less than 0? In the second and the fourth. Where is the sine function positive? They're all positive in the first. Ambitious students, S for students, corresponds to the sine function. So sine is also positive in the second quadrant. Which quadrant do they have in common? That is quadrant 2. So that was step 1, determining which quadrant we're in. The next step is to draw a diagram. I want to see what this angle measure looks like. So I know I'm in quadrant 2. I'm only going to draw quadrant 2. I also know that because I'm working with the tangent function, the tangent of theta is equal to negative 1/3, which is equal to opposite over adjacent. Now, if I'm in the second quadrant, my opposite side is going to be positive. Just watch this. Don't write this down. I'm just going to draw a random sort of triangle out into the second quadrant. The opposite side is going to be positive, and the adjacent side is going to be negative. So the fraction negative 1/3, that's hiding behind me a little bit, there we go. The negative sign that's in this fraction up here, in this fraction right here, that negative sign is next to the division symbol. It could go in the numerator, it could go in the denominator. Since I know the adjacent side is going to be negative, I'm going to move that minus sign down into the denominator and write this as positive 1 over negative 3. I'm trying to make my notes match up with the reality of the situation as much as possible so that it helps my mind make sense out of the diagram and connect the diagram to the arithmetic or the trig that's happening on the page so that it's all very well connected. Okay, so now I've got an opposite side of 1, an adjacent side of negative 3. So the adjacent side is much longer, 3 times longer than the opposite side. So I'm going to try to draw my triangle. That's maybe a little extreme. I'm going to draw my triangle as much to scale as possible. Now, doesn't it look like I might have an opposite side of 1 and an adjacent side of negative 3? That adjacent side looks like it might be 3 times longer than the opposite side. Nice, so that helps my mind to make a little bit more sense out of this. Then I have to do the Pythagorean theorem or use the distance formula in order to figure out my r value, or my h value. I'm going to label it as h instead of r. My hypotenuse is equal to the square root of 1 squared plus negative 3 squared, which is equal to the square root of 10, which cannot be simplified. So I'm going to then just go back and write in the square root of 10 into my diagram. If it's helpful for you to label the opposite, adjacent, and hypotenuse on your diagram, then you should do that. My guess is that you're going to get to the point where you won't need to do that. It does clutter the diagram a little bit, but I'm going to sneak in and do that for you anyway. By the time I get to the next chapter, I will probably stop doing this because either you will have figured out where the opposite and adjacent and hypotenuse are, and you'll still be with me, or you won't have figured them out. Things won't be going well. You might not be with me anymore. But my hope is that you nail that down and that you stick with me as we keep going through this material. This is it. We did it. The other thing I suppose we could do for this diagram is we could put in hold still. We could put in our theta value. That's where theta is. Theta prime would be inside the triangle, nearest to the origin. But the great news is that we've got a really nice diagram that we can, or that will help us answer the actual question, which is to find the exact value of the remaining trigonometric functions. We already know what the tangent of theta is, so let's find sine and cosine. The sine of theta, which is opposite over hypotenuse, opposite side of 1, hypotenuse is the square root of 10. If you'd like to rationalize that denominator, some teachers and instructors and professors require the rationalization of your denominator, some don't, but if you do rationalize it, you'll get the square root of 10 over 10. I got that by multiplying my fraction right here. I multiplied it by root 10 over root 10, and then simplified. The cosine of theta is equal to adjacent over hypotenuse, which is negative 3 over the square root of 10, which if you simplify or rationalize by multiplying by root 10 over root 10, again, you will get negative 3 root 10 over 10. Tangent we already knew. It was given to us in the problem. It's opposite over adjacent, which is negative 1/3. So we won't need to submit that as an answer. And then cosecant, secant, and cotangent are the reciprocals of these three answers. I would not take the reciprocal of those because it's going to put your root 10 into the denominator again. Take the reciprocal of these answers. That way the root 10 that was in the denominator before we rationalized will flip over, and all of a sudden it'll be in the numerator right where you want it. So I mentioned this right at the beginning of this video, and these are called the quadrantal angles. The quadrantal angles are the theta values that would swing the hypotenuse or the radius so that it ends up on one of the axes. So if you're aiming in the direction of 0, if your theta value is 0, then your hypotenuse is going to be laying right on the positive x-axis. And if your theta value is pi over 2, your hypotenuse is going to be laying right on the positive y-axis. If your theta value is pi, it'll be laying on the negative x-axis. If it's 3 pi over 2, if it's 2 pi, it'll be on the back to the positive x-axis again. And we could keep adding pi over 2 plus pi over 2 plus pi over 2, and we could keep taking that radius or hypotenuse and moving it around the circle and having it land on the axes over and over again. When you're working with an angle like pi over 4, it's easy to draw the hypotenuse out into the middle of the quadrant and then drop an altitude, and you got yourself a nice triangle. It's not as easy if you draw your hypotenuse here, and then what do? Drop your altitude next to it, or right on top of it, or see how all of a sudden diagramming those becomes really tricky, and determining the opposite, adjacent, and hypotenuse becomes really tricky. That's why I was saying it'll be beneficial for us to learn about the graphs of our sine, cosine, and tangent, our first three trig functions. We'll get the graphs of those down, and then we'll talk about creating the reciprocal graphs. And knowing those graphs is going to make evaluating these functions a lot easier. So I'm definitely not going to address cosecant and cotangent with you right off the bat. So let's do this. Let's let go of these. Let's, instead of doing cosecant of pi, let's talk about the sine of pi. And I'm going to use this as an opportunity to give you a little initial introduction to the graph of the sine function. And then we're going to talk about it in greater detail later. The sine function, as we've talked about already, has a maximum output value or range value of +1 and a minimum output value or range value of -1. You also know now, or at least you've heard, so I want you to know it, that the sine function has a period of 2 pi. And so I'm also going to go onto this graph, and halfway between the origin and 2 pi, I'll put another mark. That's going to be pi. And then halfway between that mark and the origin is going to be another mark, and that's going to be at pi over 2. So we've got pi over 2, pi, don't need a division symbol there. The next mark between pi and 2 pi is going to be 3 pi over 2, and then of course there's the 2 pi. Pi over 2, pi, 3 pi over 2. Those look familiar? There they are. North, west, south, and then back around to east. When you take the sine of 0 radians, or 0 degrees, the answer, the output value, is 0. When you take the sine of pi over 2, the output value is going to be 1. When you take the sine of pi, the answer will be 0. When you take the sine of 3 pi over 2, the answer will be -1. When you take the sine of 2 pi, which is the same thing as taking the sine of 0, your answer will be 0 again. So the graph of the sine function, at least part of it, ends up looking like this. Now the sine function is periodic, which means it repeats every 2 pi. So what I just sketched in black, you could take it and copy it, and then paste it, paste it, paste it, paste it, paste it, and you'd get another version of the graph going out here like this, and then it would repeat again and continue going off forever. All right. It does the same thing in the negative direction. That graph is going to 1, 2, 3, 4 is going to persist and come down to here, and then come back up to here, and back up to here, and back up to here. I drew those with sort of a dotted curve because I'm not trying to focus on those parts of the graph at the moment. I really just want to focus your attention on the solid part of the curve that I drew initially that bounced through those 5 points from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. All right, let's just stay focused on that for the moment. Now, let's try to answer the question. What's the sine of pi? Pi is your input value. That's your x value or your theta value. What's the y value? Well, the point at which theta is equal to pi, right, it corresponds to that point right in there. And what's the y value? 0. So what's the answer to our question? What's the sine of pi? The answer is 0. So we didn't have to draw any triangles for these. Okay, there was no SOHCAHTOA involved. All we had to do was be familiar with the graph. I highly recommend that you start committing that to memory. All right, as I said, we are going to look at it in greater detail again later. Cotangent. Let's change this one and make it tangent of pi over 2. The tangent graph looks substantially different. We have not even talked about the domain and the range of the tangent function yet, but I'm going to go a little bit rogue, and I'm going to show you what one period of the tangent function looks like. And you already know that the tangent function has a period of pi. Let's see. I'm going to put 1 mark and 2 marks, and in the negative direction, I'll put those marks also. Now this is interesting because I'm going to then put a vertical asymptote there and a vertical asymptote here. Remember that an asymptote is a line that our function does not cross. Our function is not defined at an asymptote. Usually asymptotes are caused by division by 0, so that's why they're not part of the domain. That is the case here. Now, I apologize. I didn't do anything wrong, but what I should have done, well, I'll do that the next time we talk about these functions. Okay. Where are those asymptotes? They are at pi over 2 and negative pi over 2. What's the distance from negative pi over 2 to positive pi over 2? Pi. What's the period of the tangent function? Pi. So here we're looking at one period of the tangent function. So what are those smaller marks that I put inside of there in blue? Those are negative pi over 4 and positive pi over 4. Negative pi over 4 and positive pi over 4. I wrote those labels in those specific places for a reason. Okay. What is the tangent of negative pi over 4? The answer to that question is negative 1. So I'm going to plot the point, negative pi over 4, comma, negative 1. And what is, so you need to label that, I suppose, with a negative 1 as best you can. What's the tangent of 0? The answer is 0. So I'm going to put a point. I should be doing those in red for consistency purposes. Make that red, make this red. And then what's the tangent of positive pi over 4? The answer is 1. So we need a vertical mark on the y-axis. We can label that with a 1. And then we'll plot the point pi over 4, comma 1. And then I'm going to switch to my black pen, and I'm going to sketch the curve for you. The tangent curve stays between these asymptotes, comes up and passes through these points, right through the origin, and then has to stay still between that asymptote. That's a unique graph. This entire thing that I've drawn, you could copy and paste it off to the right and off to the left also, so this graph is going to repeat just like that sine curve repeated. We're going to stay focused on the middle part of it here, and we're going to answer the question, what is the tangent of pi over 2? Now, if you look at this graph that we just drew, and you locate an x value or a theta value of pi over 2, you notice that there's an asymptote there. So what's the answer numerically to this question? There isn't a numerical answer. The answer is that the tangent of pi over 2 is undefined. That seems anticlimactic, except that if you answer undefined, you're going to get the correct answer on a homework assignment, quiz, or test. So it's kind of good that you know about that. Let me ask you a follow-up question. What's the tangent of negative pi over 4? Take a look at the graph. What's the tangent of negative pi over 4? Find negative pi over 4 on the x-axis. In this case, go down to the graph. And at that point, tell me what's the y value. If you said negative 1, you're correct. So if you want to write that down, the tangent of negative pi over 4 is equal to negative 1. What's the tangent of 0? That point has a y value of 0, so the answer is 0. The tangent of 0 is 0. And what is the tangent of pi over 4? What's the y value at that point? 1. Perfect. So negative pi over 4 and pi over 4 are not quadrantal values. Those are in the middle of a quadrant. However, negative pi over 2 points due south on the unit circle in the downward direction. That's a quadrantal angle, and tangent is undefined there. 0 points to the right on the unit circle. That's a quadrantal angle. Tangent of 0 is 0. At pi over 2, due north, quadrantal angle. Tangent is undefined at pi over 2. The one that we didn't talk about happens at pi. So we do need to draw just a little bit more of this graph so that we can include pi in this lesson. Let's go there. And we'll need... Yeah, that works. So I'm going to do a little bit of copy and pasting. I guess I should just keep going. The distance between the vertical asymptotes is a distance of pi. So this right-hand vertical asymptote, I'm going to copy and paste it to the right, a distance of pi. So pi over 2 plus pi is 3 pi over 2, which lands us here. So again, this distance is pi, this distance is pi. The second time I drew it, it's a little bit more spread out, forgive me. When we do this later, it'll be more accurate. And we need one more point up here at a y value of 1, and then we can draw our curve again that passes through those points. And we need to make sure to label these. So we had pi over 4 and pi over 2. Those are on the graph already. Then we have 3 pi over 4 and 4 pi over 4, which of course is equal to pi. So I wanted to make sure that that one was on there for you so that I can ask you the question, what's the tangent of pi? And then you can look at the graph and see that where you have an x-coordinate of pi, you have a y value of 0. Therefore, the tangent of pi is equal to 0. That's the last of the quadrantal angles for the tangent function. All right, that's a couple of intense graphs. That's the sine graph and the tangent graph. I suppose we should cover the graph of the cosine function also. So let's change this to a cosine question. How about the cosine of pi over 2? The cosine graph and the sine graph are very similar to each other. Let's put 4 marks to the right and 4 marks to the left. And then I'll tell you where to draw some. Oh, and let's go up 1 on the y-axis and down 1 on the y-axis. The rightmost point that's out here is at at 2 pi. That's that point right there. Negative 2 pi is over here. And let me show you where to draw some points so that we can draw a curve. The cosine function starts out on the y-axis with a y value of 1. As we move to the right, it comes down to cross the x-axis. It hits its minimum when x equals pi. It comes back up to the x-axis at 3 pi over 2 and comes back up to its maximum at 2 pi. So if you can, my hand's a little shaky. Let's see if I can do this. So that's 1 period worth of the cosine function. Again, you can copy and paste it off to the left and to the right, and we will multiple times as we evaluate different angle measures. Pi, 3 pi over 2, pi over 2, those are your x values, y values -1, y values +1, just like for the sine graph. So what's the cosine of pi over 2? Find the x-coordinate of pi over 2, locate that point. What's the y-coordinate? 0. What's the cosine of pi over 2? 0. What's the cosine of pi? Well, what's the y-coordinate here? -1. Cosine of pi is -1. How about the cosine of 3 pi over 2? Back up to 0. And what's the cosine of 2 pi? +1. What's the cosine of 0? Also +1. Now the cosine function has a period of 2 pi, so the output values repeat every 2 pi. What's the cosine of 0? We just said it was 1. Add 2 pi to your angle measure. What's the cosine of 2 pi? Still 1. What's the cosine of 4 pi? We added another 2 pi, so the output value is the same, +1. For 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, and so on. What about in the negative direction? -2 pi? Cosine of -2 pi, still +1. -4 pi, -6 pi, and so on. Reference angles, we've been talking about reference angles already, so I'm not going to spend, I don't know, any... all right, I see the point of those graphs. If you draw an angle into the second quadrant, we've been drawing reference angles in here, theta prime. In the third quadrant, vertical line up to the x-axis, theta prime is here. Inside the triangle, the angle nearest the origin is the reference angle. That's how I like to phrase it. I'll say it one more time. Inside the triangle, the angle nearest the origin is the reference angle. Inside the triangle, nearest the origin, there it is, the reference angle. And we call it theta prime. Oh, there it is, typed up. You can see the actual, right here, theta prime. It's not quite an apostrophe. It's like a straight apostrophe. All right, evaluate using reference angles. 13 pi over 3, that's way more than one full rotation. So we've got to bring multiple skills to bear on this problem. Where's 13 pi over 3? It's too big. Let's take out at least one full rotation from this thing. That's equal to the cotangent of 13 pi over 3 minus at least 6 pi over 3. So that's the cotan then of 7 pi over 3. That's still bigger than one full rotation. Now I took out 2 pi. I could have taken out 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, whatever. Whatever multiple pi I wanted, because the period of the cotangent is pi. So I removed, when I subtracted 6 pi over 3, I removed 2 periods from the angle measure. 7 pi over 3 is still larger than I'd like it to be, so I'm going to subtract out, gee, if I take out another 6 pi over 3, we're going to be looking good. We're going to have a very manageable angle measure. So I'm going to say that this is equal to the cotangent of 7 pi over 3 minus another 6 pi over 3, removing another 2 periods. That's an equal sign, believe it or not. So this is equal to the cotangent of pi over 3. From there, you can draw yourself a diagram in the first quadrant and evaluate the cotan function. I will do that quickly without talking too much about it. Pi over 3 is high in the first quadrant, always dropping the next leg to the x-axis. Pi over 3 is my reference angle, which I didn't draw very well. Pi over 3 is 60 degrees. That's my medium-sized angle, so it eats the medium-sized side, which in a 30, 60, 90 triangle is the square root of 3. Hypotenuse is 2, as I like to do. Short leg, therefore, is 1. It's in the first quadrant. They're all positive. Cotan is tangent is opposite over adjacent, so this is adjacent over opposite, which is equal to adjacent side is 1, opposite side is the square root of 3. If you rationalize your denominator, you get the square root of 3 over 3. So that skill of being able to subtract out some periods from your angle measure definitely came in handy. And then we drew a good diagram and answered the question. I don't want to do another tangent-related problem. Let's change this one to cosine and see what happens. Let me just say very quickly that this previous cotangent problem, you might want to write yourself an additional note. Something to the effect of the fact that ultimately we subtracted 4 periods of pi from this angle measure in order to turn that angle measure into this angle measure, which made the problem a lot more easily solvable. Here we're working with a negative angle measure on this new cosine function problem. What is the period of the cosine function? We talked about it while we were drawing the graph. The period is 2 pi. So if I modify this angle measure at all, I'm going to be adding 2 pi to it. Cosine is also an even function. I could simply erase that negative sign that's inside of there, because cosine is even. The cosine of negative 17 pi over 6 would equal the cosine of positive 17 pi over 6. And then we could be subtracting periods of 2 pi from that angle measure. But in this problem, let's just leave it negative, and we'll take cosine, the negative 17 pi over 6, and let's add to it. Let's make that angle measure positive. So I'd like to add 2 pi, which is 12 pi over 6. Well, that's not even going to make this positive yet. Let's add 2 periods to it. Let's add 24 pi. Let's add 2 times 12 pi over 6. So it's very clear that we're adding 2 periods of 2 pi. And now I need to know what negative 17 plus 24 is. Negative 17 plus 24. That's the same thing as 24 minus 17, which is 7 pi, still over 6. So we've got the cosine of 7 pi over 6. I'm so terrible at arithmetic, it's amazing. I can do many other things. Arithmetic, not my jam. I'm still nervous about 24 minus 17. Oh, we're back. Now I've got a very manageable, more familiar angle measure. I'm going to diagram this. 7 pi over 6 is a little bit more than a half of a rotation. So I'm going to be diagramming in the third quadrant. Six pi over 6 is to the left on the negative x-axis, so we're dropping down 1 pi over 6 below that. So it's a little much. That'll do. And then I will draw my leg up to the x-axis to make my right angle. This is 7 pi over 6, which means that our reference angle is pi over 6. A reference angle of pi over 6. Pi over 6 is 30 degrees. 30 degrees is the smallest angle of the 30, 60, 90 triangle, which means that the 30 degree angle will be across from the smallest side of that triangle. The small side we like to label with a 1, but since this 1 is below the x-axis in the negative vertical direction, I'm going to label it with a negative 1. The long leg of this triangle measures root 3, but since it is to the left of the origin, which is in the negative horizontal direction, I'm going to make it a negative 3, and the hypotenuse I like to use is 2. The hypotenuse, for now, is always going to be positive. Now that we've got a great diagram, we can answer our question, which was, what's the cosine of negative 17 pi over 6? Well, that's equal to the cosine of 7 pi over 6. And cosine is equal to adjacent over hypotenuse, which based on the triangle that we drew and the reference angle that we have, the adjacent side is negative root 3. And the hypotenuse measures 2. Make sure that your negative is very distinguishable from your square root symbol there. Negative root 3 over 2. That was a good one. And it's nice we get to see these problems where we have to mix multiple techniques or tools or tricks or whatever you want to call them. So we had to know about coterminal angles. We needed to know about the period of our various functions, from the cotangent function to the cosine function. We needed to know about reference angles and where to be drawing our diagrams. We needed to know the side length relationships, in this case of a 30, 60, 90 triangle. We had 2 negative leg lengths in this diagram, so that could have tripped you up a little bit. And then we needed to know the SOHCAHTOA relationship of the trig function. We have accumulated a lot of things that we need to know, and we're only 4 videos or 4 sections into this process. Definitely want to stay on top of your game. This is it looks like it's one problem. It's really like 1, 2, 3, 4, 5 problems, which is a little time consuming. We could do it, but it's really just 5 problems that are of a similar size and type to the ones that we've been working on so far. What are these problems here? This is nice. I'd rather do one of these. Okay, this previous problem, the sine of 3 pi over 2, that's a quadrantal angle. That's equal to -1. If you'd like to try that one out for yourself. The tangent of -8 pi over 3 is this. Let's see. Let's add 3 pi to it to make it pi over 3, and the tangent of pi over 3 is the square root of 3 over 1. I'm doing these in my head, so you might want to punch these into a calculator and just confirm it, but I'm pretty sure on both of those. The cosine of -5 pi over 6 swings you down and around and into the third quadrant, or you could think of it as being the cosine of 5 pi over 6. Since it's an even function, it would give you the same answer. Cosine is adjacent over hypotenuse, which is going to be -√3 over 2. Yeah, that's right. And then you've got to add all those together. So you're going to need a common denominator. So you've got -√3 over 1 plus, well, we could think of it now as minus the square root of 3 over 2, right? So I multiplied these together in order to get -√3 over 1. And adding a negative number is the same thing as doing subtraction. That's where that came from. So this is equal to that is equal to all of those things. Let's get rid of this. And we need a common denominator, so let's multiply this by 2 over 2, which gives us -2√3 over 2 minus √3 over 2, which is equal to -3√3 over 2. Just quickly, I'm pretty sure that's what the answer is. You are more than welcome to type that into a calculator and confirm that, but for the moment I'm sticking with it. I'd like you to have an answer key for these problems, and I'm still trying to figure out the best way to deliver that since I'm not working out all of these problems, so my answer in that case was to just kind of rip through it very quickly and do most of it in my head, but at least you've got something to shoot for. Now on this last page of these notes, we were trying to find an angle measure that's between 0 and 2 pi, so within one full rotation, that causes this first equation to be true. So we need the cosine to equal -1/2. And I will remind you that the cosine is equal to adjacent over hypotenuse. Now this minus sign should either be associated with either with the numerator or with the denominator. I don't know why I drew those little arrows. I could have just said that. And the hypotenuse is never going to be negative. So I'm going to bring that minus sign up and associate it with the numerator. So my adjacent side is going to be -1. My hypotenuse is going to be 2. Where am I going to have an adjacent side that's negative? Let's consider all the options. Is my adjacent side right there going to be negative? I don't think so. It's on the positive x-axis. What if I drew my triangle out into the second quadrant? Would this adjacent side be negative? On the negative x-axis? Yeah, it would. So I think it's a go for the second quadrant, but also consider what if we drew our triangle into the third quadrant? This is still the adjacent side, which is still negative. So I think we have to consider that also. This one's a no-go. So we can also think back to ambitious students take calculus. We know that here the cosine function is returning a negative value. Cosine is positive in the first quadrant because all of our trig functions are positive in the first quadrant. Ambitious students take calculus, C for calculus, C for cosine. Cosine's also positive in the fourth quadrant. This cosine function is not positive. So we have to eliminate the first and fourth quadrants, so that's another way that we could have known to consider the second and third quadrants. Right, so now we need to label this lovely diagram that I just very quickly sketched onto here with an adjacent side of -1 and a hypotenuse of 2 and a hypotenuse of 2. So we're considering two triangles simultaneously here. The Pythagorean theorem tells us that this side length over here, oh, this is going to be a 30, 60, 90 triangle. Nice. That's the square root of 3. This is negative square root of 3 for our vertical legs. And if you want to put a note in there somehow that we determined that by using the Pythagorean theorem, you're welcome to do that. A squared plus b squared equals c squared. We don't actually need those rad 3's to be there. What we need is such an intimate knowledge of the 30, 60, 90 and 45, 45, 90 triangle and the diagrams that we've been drawing so far that even without these rad 3's, the fact that we're sitting here looking at two right triangles, let's just look at one of them, the one in the second quadrant. That triangle in the second quadrant is a right triangle with a hypotenuse of 2 and a leg length of 1. I don't care that it's negative, it just means it's to the left. That, therefore, is for sure a 30, 60, 90 triangle. There's no other way to have a right triangle with a hypotenuse of 2 and a leg of 1 and not have it be a 30, 60, 90 triangle. And we know that the 1 is always opposite the smaller angle, which means that this side, which now that you know it's a 30, 60, 90 triangle, is most certainly the square root of 3, that must be across from the larger angle inside of our triangle, which means that this angle right here must be the 60-degree angle. In other words, pi over 3 radians, which means that this angle must be 2 pi over 3 radians. So the first answer for this question is a theta value of 2 pi over 3 radians that swung the hypotenuse or the radius into the second quadrant, allowing us to establish that triangle. We rotate into the second quadrant at 2 pi over 3, we draw that triangle, then we rotate another pi over 3 so that we're aiming to the left in the direction of pi, and then we rotate another pi over 3 to drop this hypotenuse down into the third quadrant. Adjacent side still -1, hypotenuse still 2. Therefore, it must be a 30, 60, 90 triangle. Therefore, the missing side must measure the square root of 3. The fact that it's negative is fine, but more importantly, the fact that it measures root 3 means that this angle right here must be the pi over 3, which we already sort of confirmed by drawing this arc and then marching forward by these additional steps of pi over 3. Regardless, 2 pi over 3 plus pi over 3 plus pi over 3 equals 4 pi's over 3. That amount of rotation is 4 pi over 3 radians. So the second answer to this question is 4 pi over 3. Are you kidding me? We've got trig function questions now that have 2 answers. That's correct. Theta equals 2 pi over 3 and 4 pi over 3. 2 answers separated by a comma. No parentheses, no squiggly brackets or anything like that. Just a list of answers is fine. Similar process here for the tangent of theta equaling -√3 over 3. And we're at the 1 hour mark on this video, so I'm going to save this one for my students in class. If you would like to attempt this one, you still can. You can work this problem out. You can draw some diagrams. Here the tangent of theta is negative. Tangent we know is positive in the first and third, so your diagrams on this one are going to be in the second and fourth quadrants. Decide, is my opposite, is my adjacent, which one of those is positive. Draw the diagram as accurately as you can. And this one's interesting. I'll give you something to consider. This fraction is also equal to -1 over the square root of 3. I have unrationalized the denominator. With an opposite and adjacent sides of 1 and rad 3, labeling your triangle using those measures, I think you're more likely to recognize the triangle and therefore the angle measures. So give that one a shot, and when you think you have a correct answer, I'm trying to come up with it real quick. -1 rad 3. That's, I think that one of your answers is 11 pi over 6. If you think that one of your answers is 11 pi over 6, then put your calculator in radian mode, take the tangent of pi over 6, and you're going to get some ugly looking answer. It'll be a terrible decimal. Then write that decimal down, at least like 3 decimal places worth of it, and then type this terrible looking fraction into your calculator and see if you get the same decimal. That's a way that you can check your answer and see if you got the right answer. All right, that's it for this one. Thanks so much for joining me. I appreciate it. How do I get out of here? All right, let's click here. All right, thanks again. See you next time.